So like I said, I'm not going to go over the ones that are like the ones just on the test, but I'm going to go over the other kinds of problems that you're going to see on this thing we do on Tuesday. Remember, this test on Tuesday, which actually you've seen actually the whole thing on when we took it at the beginning of the year. It was about half of that test I gave you at the end of the first 9 weeks. I used the ones that are appropriate from that pre-test on there. And then this is the rest of it. It is a multiple choice format. So by all means, use the strategies that you've got. When I went through it looking for, what are all the kind of things that might help you, even outside of actually knowing the content all that well, there's not really a lot. Mostly it's like, hey, if you're asked to solve an equation, do you know how to take the 4 multiple choice answers and kind of back substitute until you find one that works? That's probably about the most you can get from it, as far as I remember right now. And you will be given formulas for the same ones that we just had on this test, and then the only other formulas we used were compound interest, and that'll be on there too. So, and this review is still coming out of the orange book. It's got some things that the new book kind of took out, but there's left in this exam. So I think it's a better one for you to look off of. Determine domain and range from a calculator graph. Right? If you're just looking at a graph, you can assume when you see a parabola that's going like that the domain is all real numbers. But what is the range? It looks like the y values do not go infinitely up and infinitely down. Where do they stop? At 1, right? So in order to find a range, you would have to say domain can be all reals, but the range would be y less than or equal to 1. And I'm pretty sure, but I'm not 100% because I just don't remember the way I saw it, that they might be using an interval notation, right? Negative infinity to 1. How about this one? Is the domain all real numbers? It's not. Where does it stop? At x equals 1. So, okay, how can I write that? Domain. It starts at 1 and it goes higher. How do I write that? Okay, you could do the 1 to infinity, or if I did it like this, it would be x greater than or equal to 1. And again, this is a parabola, which actually we did this already because we did that section on conic sections. When the parabola now is laying down to the side, we can assume that it's going infinitely up and down, so it's all reals. So I believe the question is just going to give you the function. You need to put it in the calculator and look at it and be able to make that kind of judgment. Determine intervals of increasing and decreasing. Remember, a graph is increasing if it's going up from left to right. Like this graph here is increasing, and then it's decreasing, and then it's increasing. And do you remember how do we state intervals? They're intervals of x, right? You want the x values. So for example, let's just say the decreasing interval here. What's the interval of x where it's decreasing? Where does it start? At 0, right? Use the x values, right? X, and it stops decreasing at 2. So you would say that it's decreasing 0 to 2. And it's increasing. Looks like there's 2 intervals of increasing, right? It's increasing from the left side of the graph until it gets to 0. So what would I say is the left side of that interval? Negative infinity, right? Negative infinity to 0. And then what about this interval? Starts here, goes infinitely to the right. 2 to positive infinity. Okay, this graph looks like it's decreasing from the left side of the graph into here, and then it's increasing from here to here. How would you state this interval of decreasing? Left side of it is negative infinity, right side of it is negative 1, right? That's a negative 1. So you would say decreasing, negative infinity to negative 1. And the increasing is, starts at 1, goes to infinity. And you are given the graph, right? You don't even have to put it in the calculator. You're given a graph, and it's all highlighted, kind of like this. All right, graph a piecewise function. If you remember, a piecewise function is a function. I mean, the main thing here you got to keep in mind, a piecewise function is a function. Means it passes a vertical line test. You're not, this is two different graphs, but they're not going to be for the same intervals of x. Otherwise, it wouldn't pass a vertical line test. I mean, this graph right here, this first one, x plus 6, well, we know what that looks like. That's a straight line. The y-intercept is 6. The slope is 1. Right, that would look like 1, 2, 3, 4, 5, 6, something like that. Right. That is a y-intercept of negative 4 and a slope of a half. That would be something like 1, 2, 3, 4. And the slope is negative 1/2. I'm just doing this approximately, so it's something like that. But if I put both of those on the same background, that's not a function. If a vertical line would cross in more than one place. That's why we got to use this domain here, which is telling us only use this graph when x is less than or equal to negative 4. And not knowing exactly where this starts, I'm going to say, let's say that's negative 4. And let me erase this. That means I don't want this graph to the right of negative 4. And I don't want this graph to the left of negative 4, because it's only good for greater than negative 4. So it should only look like there's one line in any particular interval, right? So, I mean, I can tell you in a multiple choice test, some of your options, they got two graphs over the same interval of x. It's not a function, and it is a function. Now, do you remember how you can put something like that in the calculator? If you do this, let me clear it. Let's say we'll do the second one in the calculator. All right, this is how it works. Clear it. And let me get down here and clear it. Enter. One more. Is that right? Yeah. Get rid of this thing. It's bothering me. Okay, right. So put that on the line 1 in parentheses. Parentheses. Square root of x4 plus x, and parenthesis. Oh, that was wrong. Delete. Get out of the square root, and parenthesis. And now divide. Put a divide symbol in there. We're not really dividing. We're just separating the function from the domain. And now do another set of parentheses and put in this x less than 0. X, and where do you find the inequality symbols? Second, no, not left to the y. Second math. There's all the symbols you want to use. So for the less than, we use 5, 0. And then put the next one on this line, parentheses, the square root of 4 minus x, arrow out of that, right parenthesis, divide, left parenthesis, x is greater than or equal to 0. X, second math, greater than or equal to is a 4, 0. Now when I graph it, it only graphs one graph for each interval of x there. So the one of them is giving you from here to here, the other one's giving you from here to here. So that it does the piecewise part for you. Just put the function in parentheses, put the domain in parentheses. Remember, second math. That's where you find those. Okay. Graph absolute value function. Again, you're really being asked to identify the graph of an absolute value function. And we know that the shape of an absolute value function is a V, right? The parent function would be a V with the vertex at the origin. So really what you're trying to understand is, what is it that causes this thing to get shifted left 3? Right? The x is there. How do I make a shift to the left of 3? Plus 3. That's the shift to the left. How do I make it flip so that it's opening down? Minus. This one has got a shift of right 2, down 4. Y equals x minus 2 minus 4. Okay, evaluate a composition of functions. Remember, the composition of functions is written like f of g of x, which usually what we do, if it's f of g of x, we would do something like f of g of x. Right? Then we would take the g of x and we would plug it in. No, first we would put the replace g of x with the x squared, and then do whatever that says. If this is f of x, then put x squared in the place of x. It's the square root of x squared plus 4. I mean, in the end, it just take this for f of g of x, take this and put it into the place there. That's what you're doing. Right? If you wanted to do, let's say for the second one, if I want to do g of f of x, then take this and plug it in there. That's a composition. Now, on the test, it's not actually f of g of x or g of f of x. It's more like this. Find f of g of 4. It's actually got a number in the place, which if you've done the f of g of x, then you just put in 4 and there's your answer. But you may find it easier, let's say I use this one right there, to go f of g of 4. And if that's g of x, you can figure g of 4. Just plug in the 4 there, right? What is g of 4? 16, right? So that is f of 16. And if that's f of x, then f of 16 would be the square root of 16 plus 4. So your problem is actually a composition not of x, but of a number, which means you could actually avoid this whole finding the composition part of it. Just do this. You know how to evaluate a function. Okay, find an inverse. Remember the steps for finding an inverse. Step 1, replace f of x with y. So let's say I'm doing this one right. I'll do this one here. Y equals 3x plus 4 divided by 5. Right. Step 2, switch x and y. X equals 3y plus 4 over 5. Step 3, solve for y. So now that y is in the middle of the right-hand side, you have to solve for it. Multiply by 5. Subtract 4. Divide by 3. And then replace the y with f to the minus 1 of x. But just remember that in a multiple choice format for an inverse, it's the same. Find the inverse. Remember, when you functions and their inverses are just like the x's and the y's are switched. The domains and range are switched. So in a problem like this, let's say, just to make this work, the math work out easier, if I plug in a value of x, let's see, that's not even going to be a good one. 3 times 2. I'm trying to get one that works. Okay, let's say I put in f of 5. Right? In this one, f of 5 is 3 times 5 plus 4, 19. It's not really what I was hoping, but that's 19 over 4. Oh, sorry, over 5. I just did the same thing. Over 5. So whatever you get here, if you plug it into the inverse, you should get 5. I mean, all you do, that's all you have to do. I mean, I was just trying to find the number that made the calculation the easiest. I didn't really do a very good job of that. But in any case, take a number. A lot of times 0 is a good number, right? 3 times 0 plus 4 or 5, 4/5. Right, f of 0 equals 4/5. Okay, for which one of these when you plug in 4/5 do you get 0? I mean, that's the inverse. It has to work that way. Okay, you'll be given a function, I believe it's a quadratic, and asked for what are the x-intercepts and the y-intercepts. And there are actually, 4 sets of points that you have to figure out. If it's a quadratic function like this, do you remember how do you find the y-intercept? I mean, how do you always find the y-intercept? You substitute x equals 0. Well, when a quadratic is written in standard form like that, if you substitute x equals 0, what are you left with? Just a constant. So the y-intercept is that number. Right? Without doing anything, the y-intercept is 13, 54, 44, negative 17. Okay. How do you find x-intercepts? You substitute y equals 0. So on any particular problem, you can say 0 equals x squared minus 14x plus 54. And that's solving a quadratic equation. So how do you do that? You graph, or you factor, or you quadratic formula. I mean, you have options to include. If you're given the points, just plug them in and see which ones work. Right? No reason to get it wrong. Right? Find zeros from a graph. You'll be given a graph. Can you state what the zeros are? Here's one that's nice and clean. What are the zeros of this function? 0, negative 2. This one looks like there's a 0 at 0, and there's a 0 I can estimate. Negative 1.8 plus 1.8. Looks like we're at negative 2.5 and 0. So the main thing you're being asked is, can you look at a graph and do you know that the zeros are these points? Right? That's all you have to do. Look at the graph, state the zeros. Right? Determine the number of imaginary zeros in a function. Okay, two parts of this. Number one, how many total complex zeros are there? If it's an x to the third, how many complex zeros are there? 3. Remember, that's the fundamental theorem of algebra. It says whatever is that power, that's how many total zeros there are. Some will be real, some will be imaginary, but the total number of zeros are whatever that number is there. Right? So if I want to know how many complex zeros there are, then imaginary zeros there are, I need to know how many real zeros there are. Well, how do you find real zeros? You look at the graph. Just look at the graph. Right? If it shows up as a crossing of the x-axis, that's a real zero. So count up your real zeros and subtract from the total. I don't even know what. Let me try this one. Y equals. So 2x to the third plus 3x squared plus 18x plus 27. Okay, there's a total of 3 zeros. How many of them are real? 1. How many are imaginary? 2. That's it. Okay. Right. On the test, it asks about points of discontinuity. And in these problems in the book, they're really talking about vertical asymptotes. It's kind of the same thing. And these problems actually came from a matching. You know, if we look at, for example, one that's clean, like this one right here is going to have a point of discontinuity at -5, because if you plugged in -5, you'd be dividing by 0. This one would have a point of discontinuity at 2. It would have a vertical asymptote, x equals 2, like right there. I think that's actually this one right here. But they're saying find point of discontinuity. Right. What makes this a point of discontinuity? The fact that when I draw the graph, there's 2 parts, and I can't draw them both without picking up my pen and switching and drawing another line. It's discontinuous. Right. Right. Graph an exponential function, and really, just like the absolute value one, it's in a way it's knowing the shape. Right, that's decay and that's growth, and then knowing how it is that you affect the graph by adding numbers inside the function, after the function. Looks like I missed one there. Yeah, there was one more there. There you go. So like, what do we usually do to a graph when we subtract 2? We go right 2. What do we usually do to the graph when we add 1? Up 1. So look for the shape. These 3 are exponential growth. And so you just look for the one that's got the exponential growth and it's got the right shift in it. So I think that's pretty close to what the problem is too. I mean, in the end, it's multiple choice. So they graph this, and then you're going to look out of the 4 which one is right. And remember, you always have the option to put it in your calculator and just look and see what the graph looks like. Okay, calculate compound interest if the formulas are given. Do you remember how many formulas we had for compound interest? any, look at these here. We had one formula for when you had a finite number of compoundings. We had another formula for when it was continuous. Right? So this is the formula for if you have a certain number of compoundings. P is the principal, the initial amount. R is the interest rate as a decimal. N is the number of compoundings per year. T is the number of years. Okay, continuous compounding, similar formula, simpler formula, P, E to the R, T. Right? You don't have an N because you don't have a finite number of compoundings. So you just, at that point, you're just plugging in and calculating. And you'll be given those formulas. You just have to be able to plug it in. Remember that, for example, if the R is 2, you're going to put in 0.02, not 2. Right? Be able to convert a logarithm to an exponential form. Right? How do I convert log base 4 of 16 to an exponential? What's the base of the exponential? 4. It's whatever is the base of the logarithm. Right? What power is it being raised to? 2. Remember, the logarithm equals the exponents. Logarithms are exponents. Equals 16. Usually, for this kind of thing, to myself, I would just go 4 squared to 16. 9 negative 2 is 1 over 81. 64 to the 1/2 is 8. Just like that. Just a little muscle memory thing. Okay, graph a logarithmic function. And know the basic shape, and then how it is that it's moved around by all these things here. Now, first, the basic shape of a logarithm is like this. That's an asymptote there. And we can see that this one is being flipped, left 2, right 1. That's like negative x plus 1. Right there. So it'd be up 1, and it's actually flipped around the y-axis. So, just be able to do that. Now, you can put it in the calculator. Just understand the calculator doesn't do logarithms well. It tends to do this kind of thing. Let's say this one right there. If you look for that on the calculator, you would see this. Would just stop. Because when the calculator gets to a vertical line, it just stops graphing it. It doesn't mean that the graph actually stops, but just be aware of that. So basic, it's still, just like it was an absolute value, it was an exponential, and now it's this one. They're all basically about know the basic shape and know how they get switched, moved around the graph. Like condensing. Remember, we had 3 properties of logarithms. One was a power property, one was a quotient property, and one was a product, quotient, and power. So here's a pretty basic example of a product property. How can I combine those into one logarithm? That would be ln of 2 times x. Right? The logarithm of a product is the sum of logarithms. You split it up. Right? This would be a pretty simple example of a quotient property. Right? The logarithm base 5 of 8 over t. 8 over t. Right? The logarithm of a quotient equals the difference of logarithms. And let's say this one right here. The power property says that if you have a coefficient in front, you can move it inside the logarithm as the exponent. So that becomes log base 6 of 2x to the negative 4. So a power property takes that exponent, the power, and it moves it as a coefficient. or the reverse. All right. Solve a logarithmic equation. So remember, there's the steps for solving a logarithmic equation were this. Isolate. Convert to an exponential. Solve. So for example, this first one, what do I have to do to isolate? What's with that? The log. The 3. Right? The 3 that's multiplying. So take this, make it ln of 5x equals 10. Sorry, equals 10 over 3. Second step, convert that to an exponential. What would be the base of the exponential? What's the base of the logarithm? E. ln means log base e. So you say e to the 10^3 equals 5x. And then e to the 10^3 you can plug in the calculator. And those are all numbers there. So that's how you solve that. But again, if it's in a multiple choice format, hopefully, if you don't remember to do this, try plugging in the 4 answers until you find the one that works. And when I made the study guide for this stuff, I'm picking questions that are similar in difficulty to the ones that's on the test. In this group of problems on that page, there's way more difficult problems, but they're not asking you to do one of the hardest problems from the section. It's something that's pretty straightforward. The one thing is most of the ones that I found that were easy, they were all ln's. There wasn't a lot with different kinds of logs, because sometimes we get stuck on the ln's, like convert to an exponential, and you're not remembering that means use e for that. And solve an exponential equation. Again, the same steps, right? 1, isolate. 2, take logs, both sides. 3, solve. So let's say we do this one here. Okay, how do I isolate the exponential? Subtract 10, right? Minus 10. So we have 6x, 6 to the x equals 37. Okay, now which log would you take? It says take log of both sides, but which base logarithm would you take? Base 6. Generally the way we think is try to make the base of the logarithm match the base of the exponential. Log base 6 of 6 to the x equals log base 6 of 37. Now, what does this simplify to? X. That's why you do it, right? If these two match up, then it's all x. And then that is something that, at least with these calculators, right, you've got a log-based function. You can do the logarithm of any base. So remember that that's in the math menu. Math, scroll to the bottom. So you can do that directly. We did have change of base formulas. We can say that this is log 37 over log 6. And those are the log base 10, the ones on the front of your calculator, and you can do that. But you can do log of any base in this calculator. Okay. Find the inverse of a 2 by 2 matrix. Well, how can you find the inverse of any matrix? How do you enter a matrix in the calculator? Right? Look on the calculator. Where do you see matrix? Got a word on there. Above the x to the minus 1. Right? So second matrix. Remember, go to edit. And let's say I want to put in this first matrix, this 2 by 2, 1. Okay, what is it asking for at the top? The number of rows times the number of columns, right? 2 by 2. Okay, now put those numbers in. 3, enter. 1, enter. 4, enter. 2, enter. Okay, so quit. Okay, now using the calculator, how do you find the inverse? Bring up the matrix, second matrix, just in that first column, take 1, and now hit the x to the minus 1 button. That's the inverse. Now, what they really mean by that, but on a multiple choice test, there's no way to really make you do this, is that there is a way to do this without resorting to that. It is to switch these two and put minuses in front of those two. That would give us 2, 3, -4, -1. And then you multiply by 1 over 3 times 2 minus 4 times 1. So that would be 6 minus 4, 2. Which is 1, -1/2, -2, 3/2. Which is that. So just know how to find an inverse. You put a matrix in the calculator. I mean, it's pretty easy. And then the last is another matrix question. It says solve a system of equations here. The truth is, on the test, what it's asking you to do is, how would you turn these into a matrix equation so that you could solve it, right? What would I put in? There's 3 matrices. Let's say for this first one, right, what is this matrix if this is the system? Where do I get the numbers that I put here? It's the coefficients, right? So just in order, right? 5, -3, 2. 5, -3, 2. 2, 2, -3. 2, 2, -3. 1, -7, 8. Okay, what goes here? X, Y, Z. That's the variable matrix. And then these go on the right-hand side. So that's the matrix equation. Remember, this works because of the way matrix multiplication works. When you multiply this 3 by 3 times a 3 by 1, you're going to go across the row, down the column. 5x minus 3y plus 2z equals 2. That's that. Right? Because of the way we define matrix multiplication, this would work. And we would usually, if we were going to solve it, we would say this is the A matrix, this is the X matrix, this is the B matrix. And in order to solve for this variable matrix X, we would get X equals A to the minus 1B. So we would store that as an A, store that as a B, and then on the main screen do A to the minus 1B. That's it. But the test question is just, can you rewrite a system using matrices? That's it. Okay. And that's all those problems that I just went through. And this will be on